Okay, this is screencast number 5, and it should be the last one for Unit 4, Lesson 1. I am on page 183, and I'm looking at the sample problem where it says, do the math. It says, use the graph to calculate the average acceleration of the train between 10 seconds and 30 seconds, assuming that the train is traveling north. Okay, so for instance, we're assuming that it's headed in the same direction the whole time. It's not turning or anything. All right. If we wanted to graph, well, it's already graphed. If we wanted to find the average acceleration between 10 seconds and 30 seconds, well, that is a time interval of 20 seconds. Then we have to look at the graph and see what our velocity is at 10 seconds and what our velocity is at 30 seconds. So let's do that. Okay, that we're talking about right now, from 10 seconds to 30 seconds. Okay? All right, so I know that my time interval is 20 seconds because 30 minus 10 is 20. But then we also need to look at what the velocity does during that time. So if I look at 10 seconds, I am at a velocity of 30 because that's where the red line is. At 30 seconds, I am at a velocity of 15. Okay? 30 minus 15 is 15. Okay? So, if you look at the math up here, I know it's kind of hard to see on my copy, but you should be looking at your copy. Your final velocity is 15, and your starting velocity was 30. 15 minus 30 gives you a negative number. It gives you negative 15. Okay? Down at the bottom, the time. The final time was 30. The beginning time was 20. And that's a difference of... Sorry, final was 30 and beginning was 10. That's a difference of 20. Okay? So you wind up having... Okay, so you can see that I've simplified the calculation. Negative 15 on top divided by 20 seconds. Negative 15 meters per second divided by 20 seconds. Okay, the reason why the negative is important, because it indicates a negative value for acceleration indicates that you're slowing down. Okay? And if we started at 30 meters per second and we wound up at 15, then yes, we definitely slowed down. So that's why we have that negative value. Okay, so when you do the math, you wind up with 0.75 meters per second squared. Okay? So you're accelerating at negative 0.75 meters per second squared in the north direction, or you could say that you're just going accelerating 0.75 meters per second south, because south is opposite of the direction that you're traveling. Okay, now we need to look at the velocity versus time graph, and we're going to do several things to kind of break it down before we answer question number 22. Question number 22 says find the average acceleration of the train between 80 seconds and 100 seconds, assuming that it's traveling north, so assuming that it hasn't changed its direction. Remember that our average acceleration is the difference in velocity divided by the difference in time. And a velocity versus time graph shows acceleration. Remember a couple of pages ago we did distance versus time graphs, which showed speed. Okay, so now we're going to do a velocity versus time graph, but they work kind of the same way. I'm going to look at this particular graph, and I notice that there are 1, 2, 3, 4, 5 different sections of the graph, and so I'm going to analyze each one of those separately. That's not actually what we need to do to answer number 22, but I do want you to do that so that you understand how you can find the acceleration at any point on this graph. Okay, so just give me a minute. We're going to mark it all up. So hang on. Okay, so the first thing that we're going to do is we'll actually answer question number 22. We're looking at the part of the graph from 80 seconds to 100 seconds, and I have marked those with a dashed line here and here. Okay? Now, I'm looking at just that part of the graph. I notice that in this little part of the graph, my velocity changes from 0 at the beginning to 20 at the end of that little portion of the graph. So my change in velocity is 20 meters per second. I also notice that there is a change in time of 20 seconds as well. So my acceleration, the answer to number 22, change in velocity divided by change in time, that's going to be 20 meters per second divided by 20 seconds, and 20 divided by 20 is 1. So I get 1 meter per second squared. Now, I'm going to look at my 5 segments of the graph, and I'm going to determine the acceleration for each one of those segments. Okay? The first one I color-coded is kind of skinny because it's only a 10-second interval. It goes from 0 to 10 seconds. Okay, but I notice that my red velocity, my red graph line is horizontal. Remember that a horizontal line on a distance versus time graph meant that I was stopped, that my distance wasn't changing at all. Well, on a velocity versus time graph, you have a similar situation. It means that your velocity isn't changing at all. And if your velocity isn't changing at all, that means you're not accelerating. So let's look at the first calculation for the first part of this graph. Okay. We get the acceleration. At the end of this time interval, the velocity was 30. At the beginning of the time interval, the velocity was 30. So that's a change of 0. And 0 divided by a 10-second interval, and that is 0 meters per second squared. So this first part of the graph, the object is not accelerating. Then we look at the second part of the graph from 10 seconds to 50 seconds. Okay, that is a 40-second interval, and I notice that my velocity over that time interval goes from 30 all the way down to 0. So 0 minus 30 divided by the 40 seconds that it occurs in, and I get negative 0.75 meters per second squared, which should make sense because up here you were being asked to find the average acceleration between 10 and 30 seconds, which is in this part of the graph. So the value was the same. Okay, then I have from 50 seconds to 80 seconds, my graph is a horizontal line again, which tells me that my velocity is not changing. So you might be able to guess what the acceleration is going to be for this one. Okay. If my velocity starts at 0 for this little red portion of the graph, and it's at 0 at the end of that portion, then it hasn't changed and it's 0 minus 0. So this part of the graph, my final velocity minus my initial velocity, that's going to be 0. Divided by a 30-second interval, but that's 0 meters per second squared. Okay. Then I look at the next part of the graph, the next, this is probably the longest time interval we have. It's from 80 seconds to 130 seconds. So that is a 50-second time interval. During that time, the velocity started at 0 and ended at 50, so that is a change of 50 meters per second, and that took place over 50 seconds. So here we go. Our acceleration in that part of the graph is 1 meter per second squared. And then last but not least, we have the last 30 seconds where it's a horizontal line again. Okay? So it's going 50 meters per second at the beginning of that time interval. It's going 50 meters per second at the end of that time interval, so the velocity didn't change. So its acceleration is 0 meters per second squared. So if you look at this graph, there are 3 sections for this particular graph. There's 3 sections where the line is horizontal, and that's going to be no acceleration because the velocity is not changing. And then the purple and kind of light blue sections, the purple section had a negative value, which told you that the object was slowing down. And the kind of bluish section, the object was speeding up. My value was a positive value. Okay, you're going to see more of these. We will be doing some more of these as we go through this unit. There's actually one at the end on the lesson review that we may look at eventually. But these are really important for you to understand. And the velocity versus time graphs and the distance versus time graphs, they're not the boogeyman. It's just you have to kind of look at them and sort of break them down into their individual graph parts and deal with those individual graph parts by themselves. Okay? Now, I could ask you, you know, what is the average acceleration for this whole entire graph as a whole? And that would be a 160-second time interval, and the velocity only changes by 20 in that time interval, so it would be 20 divided by 160. So you're not going to get a whole lot of acceleration, but that, you know, that would be like if you considered the whole entire thing as one. But if we want to know what's going on in these smaller sections, then we have to break it down section by section on the graph.